All right, I'd like to welcome Chris Stark from the um, NASA Goddard. Tonight's presentation is NASA's search for other Earths from Hubble to Webb and beyond. Is there life elsewhere in the universe, or are we alone? Humans have been asking themselves this question for millennia. Amazingly, we have an answer within our lifetimes. Come hear about NASA's plans to find planets around other stars, including some that could closely resemble Earth. This talk will review what we have accomplished so far in the search for new planets, highlighting the contributions from NASA's space telescopes, including Hubble and James Webb Space Telescope. It will then present NASA's future missions, including what may be the most ambitious space telescope ever considered, the recently announced Habitable Worlds Observatory. Join us as we discuss the search for other worlds, possibly life on other planets, and how one of our most profound scientific questions could finally be answered. I'm going to turn it over to Chris. You can take over and show what your presentation.
All right. Let me share my screen. Thanks so much for the introduction. It's a pleasure to be with you here tonight. I actually just gave the same talk in a planetarium, so I'm a little bit disappointed I can't be there in person to give it. It's always more fun in person. But you know, my in-laws actually have a place in Naples, so it's possible that someday I can make the trek over there if I'm down there. I wanted to start off tonight with a memory that I have from when I was 16 years old. And it was when I got my driver's license, and all my friends were getting their driver's license. And, you know, when you're a teenager and you get your driver's license, it's sort of like your ticket to freedom, right? You get to go where you want, when you want. You kind of get to do what you want to some degree. And growing up in Cedar Rapids, Iowa, unfortunately, there wasn't a lot for a 16-year-old to do. And so usually what we'd do is we'd just drive around. We'd get in the car, we'd go see if our friends were home, they'd pile in the car, and we'd go for a drive at night. This was all before cell phones and internet. I'm sure many of you have very similar memories to this. And one night we went out to the Eastern Iowa airport. And there was this little gravel road that we pulled in next to the fence of the airport. And we were going to watch planes fly in, land right overhead from us. But we got out there and realized pretty quickly that there's not a whole lot of traffic going in and out of the Eastern Iowa airport. But instead, we noticed that there were a lot of stars. And so we basically spent the night stargazing. And that was the night that I had that thought. I was looking at a star and the thought crossed my mind, I wonder if there's a planet around that star, and I wonder if there's life on that planet. Now, for me at the time, this was like a really profound thought. And I maintain that it is still very profound. It's why I'm at NASA now. It's sort of my motivation for going into work every day. But it's not a particularly unique thought, right? So I'm sure many of you in the audience, I can't see you right now. I'd normally ask you to raise your hands if you've had this thought. I'm sure if I were there, I'd see that many of you have had this thought. In fact, this thought is so common that you know who else had this thought? These guys. In the 5th century BC, Democritus was the first person in recorded history to think about whether there are other planets out there like Earth that potentially have life on them. 5th century, thousands of years before Kepler, Copernicus, and any sort of space program. These thoughts were going through our minds. Democritus, you know, we don't have a lot of records directly from Democritus, but we have snippets of what his teachings were from some of his followers. And so Metrodus said, it seems absurd that in a large field only one stalk should grow, and that in infinite space only one world exists. Yes, they thought space was infinite. They thought there were other worlds out there, some of which might have life on them. One of Democritus's followers, Epicurus in the 4th century BC, added to these ideas quite a bit. And one of his ideas was recorded by Lucretius in a very nice poetic sense. It must be confessed in other realms there are still other worlds still other breeds of men, and other generations of the wild. This is all in the 5th century. How is it possible that for the last 2,500 years, we've all been independently asking ourselves this same question? It's as if it's in our DNA. And tonight, I'm going to tell you about that 2,500-year search for an answer to that question, are we alone? And it's going to be a story that's full of wonder, kind of like, what I was experiencing out in the middle of the cornfield looking at stars that night. But it's also a story full of frustration, because every time, obviously the Greeks did not have the tools to test any of these ideas, right? And every time that we think we've invented a tool recently to try to find an Earth-like planet, we have failed. It's almost like the universe doesn't want us to find them. And I'll talk about some of those frustrations and problems tonight. But in tonight's story, there's a twist. And that twist is the Habitable Worlds Observatory. This is NASA's future flagship mission. It is potentially the most ambitious space telescope ever designed by NASA. And it has the specific goal of finding Earth-like planets and searching for life on their surfaces. And this brings me to the title of my talk, NASA's Search for Other Earths, from Hubble to Webb and beyond. So I talked about the Greek philosophers a little bit there. I will return to them at the end of the talk. So if you're a fan of ancient Greek philosophy, stay tuned. But I'm going to fast forward a little bit to when NASA gets involved, to the year 1990. And that's when NASA launched its first astrophysics flagship mission, the Hubble Space Telescope. Now, the whole point of Hubble was to get above Earth's atmosphere. If you are an astronomer from the ground, I'm sure many of you are familiar that when you're trying to observe stars or planets, the atmosphere interferes with our ability to produce crisp images of them. And that's because the turbulent air, not only does it throw our planes around, but it makes our images blurry from the ground. So we wanted to get above the atmosphere so that we could get the most crisp images of the universe that we had ever seen. Now, Hubble was incredibly ambitious. It's the size of a school bus. In today's dollars, it would have been billions of dollars. And so this was a major, major investment that took decades to produce. Fortunately, when Hubble was launched, everything went perfectly and everybody was happy. I'm sure you're familiar with the story that is not the case. And when Hubble took its first image, we realized that we had a major problem. The images were much blurrier than expected, and the entire point of getting Hubble up there now seemed like it was unattainable. There was a problem with Hubble's primary mirror. It had been polished incorrectly, and all of the images that it were returning were, in effect, out of focus, for lack of a better term. This was a major public failure for NASA, and the headlines started rolling in. Trouble continues to plague orbiting Hubble telescope. Scientists assess the Hubble loss and the trouble with Hubble. I actually like that last one. It's pretty clever. NASA could have said this is a loss, right? We're moving on to another mission, thrown our hands up and said we're taking the Hubble Space Telescope as a loss. I'm glad they didn't. They spent the next 3 years diagnosing what was wrong with the Hubble Space Telescope and coming up with a way to fix it. Now, this is a pretty interesting story because, as you can imagine, it's pretty difficult to figure out what's wrong with your telescope when you can't go up there and measure anything in it, right? We can't send astronauts up there with a bunch of lab equipment. They can't possibly figure out what's wrong with it. We can't bring it back down to the ground to look at it. And so what NASA did is we had 2 different teams figuring out how to fix this telescope. The first team was going down more of a traditional path. I've heard it described as optical archaeology, where they were going through all of the lab records of all the measurements they had made on every single optic, and they were trying to piece together where things went wrong. But there was another team of people that said, I think we have another way, a better way of figuring out what is wrong with Hubble. And that is through a really ingenious method called phase retrieval. And what they realized is that they could use the Hubble Space Telescope, they could observe a star with Hubble to figure out what was wrong with Hubble. And so I'll briefly explain how phase retrieval works. This is the image of the star that they obtained. And as you can see, it's not a nice, tight point of light that you'd expect a star to be. Instead, we have all of this messy, these diffraction features coming off here, which is telling us that there's something wrong with the telescope. Well, the way that phase retrieval works is you have a computer model of the telescope, of all the optics in the telescope, and you feed the computer model a guess as to what you think is wrong with the system. And then that computer model will calculate what the star would look like if your guess was right. Okay, so this is their guess as to what the star would. Can you see my cursor, by the way? I'm going to assume you can. On the right. And basically, you can compare. You can see that you didn't get it right on your first guess, but you can compare the simulation of what the star should look like to what the observation actually is. And by comparing those, you can come up with a second improved guess. And if you iterate this process over and over and over again, you will eventually converge on an image that looks very, very similar to the observation. And it will then tell you, your model will then tell you what's wrong with the telescope. Now, at the time, this was a brand new idea. NASA was very wary of it. And one of the reasons they are wary of it is because there's actually no way to mathematically prove that it finds the right solution. So you can come up with a solution that looks pretty good, and it might be completely the wrong problem with the mirrors. All that the phase retrieval folks could do was estimate the probability that they had arrived at the right solution. And at the time, the idea of computer algorithms telling you the probability that you had the right solution was all kind of foreign to NASA. And so this was very scary and untested at the time. But as it turns out in the end, phase retrieval actually diagnosed Hubble better than the optical archaeology methods. And when they went back and looked at all of those records of how they had measured, of all the optics they had measured in the laboratory, they found out that they had polished the mirror wrong by about 1.3 millimeters. And we still don't quite know why that's the case, but the best guess as to why Hubble was polished incorrectly is due to a fleck of paint. This is an image of the metering rod that was used to measure optical spacing of test equipment to actually test that Hubble was polished correctly. And on the image on the left, you're looking at the end of the rod, and you can see there's that spot in the middle that's very bright. This is because a small fleck of anti-reflective coating had been chipped off of the end of that rod. And when they used optics to measure the length of the rod, that very reflective part, they think, led them to the wrong measurement. And then so they had the wrong measurement for the rod. And when they used the rod to measure the telescope, then they ended up polishing the telescope to the wrong prescription. All of this likely due to an incorrect fleck of paint. Well, once they had diagnosed the problem with Hubble, they were able to create new optics to correct it. During STS-61, a new instrument was installed on Hubble, as well as COSTAR, which are optics that correct the eyesight of the remaining instruments. And Hubble was brought into focus for the very first time. So we went from this very blurry image on the left to this, the crispest image of the universe that we had ever obtained on the right. Once we had proven that Hubble was fixed, the floodgates were open to all of those fantastic Hubble images that you are used to. These are the pillars of creation. This is a dusty nebula in our own galaxy, in the Milky Way galaxy. This is a cloud of gas and dust that is slowly compressing. And by doing so, it's forming stars within this cloud. So especially out in the tips of these pillars, there are collections of baby stars being formed. The reason that they look like pillars is because outside of this image, to the top right, there are these massive stars that are irradiating this cloud, blasting it with ultraviolet light and slowly eroding that cloud of dust and gas. So eventually, these baby stars will emerge from these dusty cocoons at the tips of those pillars. Not only could Hubble observe star formation in our own galaxy in unprecedented detail, it could observe it in other galaxies. This is the Sombrero Galaxy. It's a relatively nearby galaxy, and it is composed of billions and billions of stars. So many stars that the inner regions of this galaxy appear like a very smooth halo of light That glow that you see is actually due to individual stars collectively contributing to the light in the image. You can also see these dusty lanes of material in this galaxy. Those dusty lanes are very similar to the pillars of creation in our own galaxy. This is where stars are being formed in the Sombrero galaxy. For my money, the single most impactful image that Hubble has ever obtained is something called the Deep Field. Many of you have probably seen this image. And the Deep Field is this fantastic experiment that was run by astronomers where they decided we want to point the world's most expensive space telescope at a patch of sky that has no known objects. And we want to stare at that empty patch of sky for 10 days. An enormously costly observation. But what they got back was nothing short of revolutionary. This is that empty patch of sky. It is anything but empty. Every smudge of light that you see in here, every dot that you see is not a star, well, with exception to maybe two there. They are all galaxies, each with billions of stars in them. And when I first saw this image, honestly, quite honestly, it still takes my breath away looking at it, but I could not help but think of that question, that 2,500-year-old question, are we alone, right? If there are billions of galaxies out there, each with billions of stars in them, what are the odds that there's another Earth-like planet out there? It's almost like, what are the odds that there isn't another Earth-like planet out there? Now, around this time, this was all mere speculation, because right up until about the time that this observation was made, we hadn't even seen a planet around another star yet. We didn't even know that they existed. It was all speculation. But that all changed in 1995. In 1995, this plot was published. This is a plot showing the detection of the first exoplanet. It's around a sun-like star, roughly speaking, called 51 Peg. So we call the planet 51 Peg B. And this plot went on to earn Michel Mayor and Didier Queloz a Nobel Prize in physics because it shows the indirect evidence of a planet around that star. And to get you to appreciate what exactly you're looking at here, I'm going to take a quick aside to talk about a brief physics lesson that will actually come in handy for the rest of the talk, because there's something fundamentally extremely important to astronomers. There's a piece of data that we value very, very much. We call that a spectrum. And so I want to talk about briefly what a spectrum is. If you take a white light source like an incandescent flashlight, like I've shown here, and you shine that maybe on a disk with a small hole in it, and you, in one way or another, focus this light down to a beam, and you shine that beam into a piece of optics, maybe like a prism, that prism will separate that white light into all of its component colors. So white is not a color. White is the combination of all the colors of light. And if you use particular optics, like a prism, you can separate that white light into all of its colors. What you get out in the end obviously looks like a rainbow, and that's basically what a spectrum is. It's a rainbow. Now, astronomers like spectra not because we appreciate rainbows more than the average person, but it's because spectra can actually tell you about what an object is made of. And so if we replace this flashlight with, let's say, something like a star, and we shine that starlight through this prism, we're not going to get a nice smooth spectrum out in the end. Instead, what we'll get is a smooth spectrum with very specific colors of light removed. And this is because the atoms and molecules on the surface of that star, they all absorb very specific colors of light. Quantum mechanics actually tells us this, and it tells us that every atom, every molecule has a unique fingerprint that it leaves in the spectrum of a star. And not only can we learn about the fact that this star has hydrogen and helium and oxygen on its surface, but we can actually study how much of that material there is. So this is an incredibly powerful type of observation to make. And Didier and Michel Mayor, they were looking at stellar spectra just like this, but they actually weren't interested in what the star was made of. What they were doing is they were observing these very specific, we call them absorption features, these missing colors, and they were monitoring them very, very precisely. Because as it turns out, when an exoplanet orbits a star, not only does the star gravitationally tug on the planet, but the planet's tugging back on the star. And that means that the star will ever so slightly wobble around in the sky as the planet orbits it. As the star wobbles, it turns out that these lines will move back and forth a little bit. And the motion of those lines tells you the speed of the star toward and away from us. So this plot that they have here is a plot of the speed of the star as a function of time. And you can see the stars coming toward us, going away from us, coming toward us, going away, and it kept repeating. And that meant that there was something gravitationally tugging on the star in orbit around the star, and they could even measure the mass of that. They had the first indirect evidence of the existence of a planet. This revolutionized astronomy. I am effectively a child of exoplanets. I am one of the first generation to grow up knowing that planets existed around stars. And shortly after this was published, many other planets were discovered using the same method. We call this the radial velocity method. And soon there were dozens and dozens of planets detected with the radial velocity method. And maybe just a few years into this, these individuals that were finding planets with the radial velocity method realized that they were going to run into a problem. And that problem was stellar activity. Stars are not these nice quiescent objects. They are these boiling, churning masses, and the surfaces of these stars are very active, and materials constantly, being shed from the surfaces. This stellar activity makes measuring the velocity of the star very, very difficult. Okay? It basically makes our data noisy and makes it impossible to find planets as small as the Earth. So we had this new technique to find exoplanets, and we realized we were going to hit a brick wall and be unable to find an Earth-like planet around a sun-like star. We have been stuck at this level for the last roughly decade. We have been unable to find an Earth-like planet with this method for on the order of 10 years. Things really haven't improved much in our ability to find radial velocity planets. There are some ideas on how to improve things going forward. We'll see if they pan out. But this is the first instance where we had created a tool to find Earth-like planets and then been foiled by the universe and our ability to do that. Once exoplanets were discovered, people started coming out of the woodwork with ideas on how to find exoplanets. And I remember being around when a lot of these ideas were floated. Some of them were kind of wacky ideas, and some of them turned out to be brilliant and incredibly productive. One of the most successful methods to find exoplanets is something we call the transit method. And with the transit method, you're not looking for the wobble of the star. What you're doing is you're observing so many stars that you can get lucky. And one of those systems can happen to be aligned edge on, as we see it. If it's aligned edge on, then when the planet passes in front of the star, that planet will block a little bit of the starlight. And that star will appear temporarily a bit fainter, right? And it will dim just a little bit for maybe 30 minutes while the planet is transiting in front of it. So if you see a star that dims repeatedly, you can infer the presence of the planet. The first transiting exoplanet was detected 5 years after the first exoplanet was ever detected. It was detected by David Charbonneau. This here is a plot showing the brightness of that star as a function of time. As you can see, it dips to about, a little more than 1% of its light is lost, and it has this very predictable, almost rectangular shape, and then it returns to its original brightness, and this happened over and over again. In my opinion, the most amazing thing about this detection, this discovery, is how David did it. David wasn't using the Hubble Space Telescope to make this observation. He wasn't using a space telescope at all. He wasn't using some huge 8-meter ground-based telescope. David Charbonneau detected this planet using a 4-inch telescope from a parking lot. I'm not making that up. This is actually a picture of his setup, but it wasn't too different from this. I think he had a wooden shed that he was inside of. So this was bare bones astronomy that anybody can do from their backyard. And in my mind, this is astounding. This just speaks volumes to the idea that there are always discoveries to be made out there. You just need to know how, when, and where to look to find them. In fact, we've been doing photometry that is precise enough to find planets like this since the early 1900s. It's just that nobody stared at stars long enough to find these planets. And, I can't help but wonder if we had found exoplanets 50 years earlier, I kind of feel like we might be in a little bit different of a world. Now, Hubble is not good at discovering transiting exoplanets, but Hubble was there ready and waiting to follow up on them because some people realized that you could use Hubble in a very particular way to learn about the atmospheres of those planets. And so what I'm showing you here are 10 spectra of the atmospheres of the planets. You see, when the planet transits in front of the star, the molecules and atoms in the planet's atmosphere will absorb some of that starlight. So you get the fingerprint of the planet now on the star spectrum. What I'm showing you here is, instead of showing you like a rainbow with individual lines removed, instead I'm just plotting its brightness. So all these little bumps and wiggles that you see in the plot tell you about particular atoms and molecules. And so you can see some of them are labeled here. So Na is, we've detected sodium and potassium, and H2O is water. We've detected water vapor in the atmospheres of some planets. But you'll notice they all look different, right? So we're starting to realize that every exoplanet is this unique little snowflake. One thing that we started realizing immediately, what we noticed is that the spectra are flatter than we expected. And what that is telling us is that there's likely a haze in the atmospheres of many of these planets. So in other words, it's very difficult to see down to the interior regions of the atmosphere. There's some layer of material that's sort of blocking our ability to probe deep into the atmosphere. And this has been a continuous problem for transiting exoplanets. In 2009, NASA changed its approach, and it really got on board the exoplanet, or the transiting exoplanet detection train. And we launched what was called the Kepler mission. Now, Kepler was not a general purpose observatory like Hubble, right? Hubble is an observatory that anybody in the world can apply to use, and a collection of professional astronomers get together, they review all the proposals and decide whether time should be awarded to a given observation or not. Kepler does not have that, did not have that. It's not a general purpose telescope, and I'm glad it wasn't, because there is no time allocation committee in the world that would ever allow you to use Kepler like they used it. They stared at the same patch of sky shown here in a series of rectangles. They stared at that patch of sky not for hours or days or weeks or even months. They stared at that patch of sky for years continuously. There are more than 100,000 stars in that patch of sky. And by monitoring the brightness of those hundreds of thousands of stars continuously for years, they revolutionized exoplanets. They discovered thousands of confirmed exoplanets and completely changed our picture of what exoplanets might be like. We now know that exoplanets are fantastically diverse. In fact, we've detected planets that are so close to their host stars that not only do they orbit in less time than it takes to watch the Lord of the Rings trilogy, but they're so hot that their atmospheres are actually being stripped off of their surface. Okay, so on the left here, I'm showing you actual data here. This is the transiting light curve of an exoplanet, and you see this nice sharp dip as the planet moves in front of the star. That dip comes back up, but then you can see this extended tail on the transit. What that is atmosphere from the planet that is being evaporated and boiled off of the planet. After the planet has passed in front of the star, that atmosphere is still there absorbing starlight. And so it might look something like the artist's picture on the right. We've also learned that one of the most common types of planets in the universe is completely foreign to us. We have no analog for this in the solar system and know almost nothing about them. So these are planets that are between roughly the size of Earth and the size of Neptune. So if you're sort of on the upper end of this, we tend to call them sub-Neptunes. If you're on the lower end of this, we kind of call them super-Earths. We know very little about these planets now. We're just starting to learn about them with the James Webb Space Telescope. One thing that we have learned is that we think the transition from rocky worlds to gas giant worlds is right around 1.4 times the radius of the Earth. Once you get much above that radius, it seems that planets just accrete a lot more gas and have very, very thick atmospheres. This is a plot that astronomers really like to show each other, but I think is really helpful for you to understand kind of the diversity of exoplanets as well. So this is a scatter plot where every point on here represents one planet. And the y-axis here, I'm plotting that planet's mass in Jupiter masses. And on the x-axis, I'm plotting the period of that planet, how long it takes it to go around its host star. And all of the red circles are planets that were discovered with the radial velocity method, looking for that wobble of the star. All of the green squares are planets that were detected with the transit method, where the planet passes in front of the star. And you can kind of see some interesting structure in this plot. It doesn't just look uniform. You can see, obviously, there's a gap between the green and the red. We don't think that's real. We think that's just a bias between the transit method and the radial velocity method. And this is a region where neither of them have been super successful yet in finding planets, basically. But you'll notice that there is a gap in the green region. And I'm pointing to it right now with my cursor. You can see about halfway down this green region, there's a gap where there's relatively few exoplanets. This gap is real. And we're not sure why it's there yet, but it's telling us something about planet formation. And the best guess as to what is going on right now is that you'll notice that all these planets have periods less than about 10 days. These are incredibly short period planets. And what we think might be going on is that planets in this upper blob, as they approach their host star, their atmospheres are being stripped off and they're transitioning very quickly down to this lower population of planets. So they're basically skipping over that space, and the planets down in the bottom left are just residual cores of planets, if you will, that have lost much of their mass. One of the most important things that the Kepler did for us is allow us to estimate the fraction of stars that have a rock roughly the same size as Earth at just the right distance where liquid water might be on its surface, okay? So this is a number people call eta Earth, if you're familiar with it. And it's a number that's incredibly important to astronomers because it tells us how many candidate Earth-like planets are out there. We don't know if they're Earth-like, but they might be Earth-like. So they're roughly the size of Earth, and they're not too hot where their atmosphere would be boiled off. They're not too cold where liquid water would be frozen. They're in that Goldilocks zone where water could be liquid on the surface of the planet. And if you look at this chart here, in 2009, when Kepler was launched, just a year or two later, some data came out from Kepler, and Andrew Youden was the first one to estimate what eta Earth was. And you can see his estimate over here. And you can see for the next 7 or so years, the estimates were bouncing all over the place. And this is because more data kept coming down. We weren't very good at working with the data. We didn't understand how to analyze it right. And we got much, much better at working with the data sets over the next 7 years. And as you can see, since about 2019, these estimates have really started to converge. And the current best guess on how common potentially Earth-like planets are is roughly 1 in 4 stars has an Earth-sized rock in what we call the habitable zone. 1 in 4. And I don't know about you, but I think about that deep field image with all those billions of galaxies, billions of stars, and we now know that 1 in 4 of those stars has a planet that might be like Earth. I like our odds. So unfortunately, if I go back one chart, you'll see on this plot here, there's an E. That's where an Earth twin would be. And you can see that there's no green dots right next to that. Kepler actually did not find an Earth twin. The reason it didn't find an Earth twin is because of the same problem. So sun-like stars ended up being a bit more active than we had realized. And all of the stellar activity created a lot of noise in our data and made it much more difficult to find small exoplanets. So Kepler We had this new mission whose goal was to find Earth-sized planets around sun-like stars, search for Earth twins, and it just barely couldn't do it again due to stellar activity. It's almost like the universe does not want us to find these. We are now entering an era of exoplanet characterization, and that era started in 2021 on Christmas Day with the launch of the James Webb Space Telescope. So I was Deputy Observatory Project Scientist for the James Webb Space Telescope, and I took part in commissioning the telescope and was working on my particular operations during launch. Unfortunately, this was during the pandemic. And so much of our team, believe it or not, was stuck at home watching it live on TV, just like you. The only difference was we had a voice loop, on in our bedroom, talking with the team, the limited team that was allowed to go into the Mission Operations Center. This was simultaneously the most terrifying and a thrilling moment of my career and quite possibly my life. Fortunately, the launch went very well, and we then had a live feed showing the James Webb Space Telescope as it separated from the rocket fairing. When I saw this the day of, I was sort of caught up in the excitement that we had just had a very successful launch, and this was just I was overjoyed to watch this, to be quite honest. But now when I go back and look at this, I can't help but think about all of the people that physically had their hands on this amazing piece of engineering. So all of the technicians that were literally soldering wires by hand to make this, all of the engineers that worked around the clock to design it and test it and make sure that it worked, and all of our partners in private industry that were designing widgets to build this machine. This was the last time that human eyes saw the James Webb Space Telescope, and I imagine for those people, this was a really profound moment. Now, something that happened during this live feed that many of us did not expect was that we were able to see the solar array deploy. So you can see that deploying right there. Many of us had not anticipated that it would deploy that early, but this was an amazing success for the mission. We heard on our voice loops that the mission was power positive, which means that we are now making our own power. Up until that point, we were relying on a battery. And if, once that battery was used up, it was used up. So if we did not start producing our own power very quickly, we would not have had a mission. So this marks a huge milestone in the launch of the James Webb Space Telescope. Now, if you're familiar with JWST, it is so large that it had to be folded up to fit in the rocket fairing. And it then spent months unfolding on its way out to what we call the second Lagrange point, where it currently resides in space. Because it was so large, to fit it in the rocket, we couldn't make it out of one mirror. We had to make it out of 18 separate hexagonal mirrors. Fortunately, we learned a lot from the Hubble Space Telescope. So here, every mirror is individually positionable. It has 7 degrees of freedom. So we can literally tip and tilt each mirror. We can rotate them. We can piston them in and out. We can even change the radius of curvature on the mirror. So even if we had made a mistake on the ground, we had many degrees of freedom to try to correct for that once it was in the sky. Fortunately, no mistakes like that were even made, and the telescope is working even better than we expected. But I was part of the wavefront commissioning team that designed some of the programs to help align these mirrors. You see, when it's in the rocket is shaking the telescope, and then when everything deploys and unfolds, those individual segments are no longer aligned like a perfect mirror. So we had to spend months figuring out how to get each of these little mirror segments to line up with one another, right? So in other words, we had to use JWST to make observations, and from those observations, we had to figure out what was wrong with the telescope to correct it. Now, what algorithm do you think we relied on to do that? Phase retrieval. And I love that arc. The very same thing, the very same algorithm that was invented to fix the Hubble Space Telescope is now the algorithm that is used to align telescopes on the ground and telescopes in space ever since. I love that thinking, right? NASA took what was a failure and built off of it and created something that would benefit all future generations of telescopes. Well, once JWST was aligned, we started getting these fantastic images. I'm sure you have seen some of these. This is probably the most famous image of the James Webb Space Telescope. We call this the cliffs of creation. No, cosmic cliffs, I believe. And this is another dusty nebula. So you're sort of seeing the interface between that dusty cloud and open space. And my favorite part of this image is if you look real close, you can kind of see these little wispy features coming off of that cloud. What you're seeing there is you're actually seeing gas and dust being evaporated off the surface of that molecular cloud due to those massive stars. So JWST has such good resolution that it can make out individual streams of material coming off of that cloud. JWST has also observed the pillars of creation, just like Hubble. These are the same pillars of creation, it's just at a bit of an angle. And you can see they look radically different from the Hubble images. You see all of these red dots in here. Those are the individual stars that are forming inside of the pillars of creation. Okay? JWST observes in the infrared, and one of the main motivators for that is because infrared light can actually see through dust. So we are able, to some degree, to make out the stars that are inside of those dusty columns and observe star formation. But probably the main reason why JWST was designed to work in the infrared is to observe galaxies that are even fainter and farther than those observed by the Hubble Space Telescope. This is one example of how JWST can observe some of the most distant galaxies in the universe. What you're looking at in this image, ignore this very bright star up here in the image. Kind of in the center, you see this cluster of white diffuse objects. This is a supermassive galaxy cluster. And to the sides and all around in this image, you can kind of see these weird things that look like distorted galaxies, like they've been stretched out. What that distorted galaxy is it's actually a regularly shaped galaxy, just like our Milky Way, but it is much, much farther in the distance, and it's actually located behind the supermassive galaxy cluster. You see what's going on here is that galaxy cluster is so massive that it's actually distorting space. And the galaxy behind it, the light from that galaxy ends up getting lensed around that galaxy cluster. That lensing process, the bending of light, distorts the galaxy, makes it look like it's in this weird shape. It also magnifies it, so it looks much larger than it would otherwise be. It's like having a magnifying glass. And it also amplifies it. It makes it appear much brighter. So normally we would not be able to observe this galaxy easily, but here it just pops right out in the image. And if you look closely, you can see individual little points in this galaxy. These are individual massive star clusters in that galaxy. We're actually picking out individual clusters of stars in one of the most distant galaxies we've ever observed, which to me is just mind-boggling. Now, JWST was not originally designed to observe exoplanets from the get-go, but as it turns out, it is an exoplanet characterization machine. When you design an observatory to do what it does, you can do all sorts of other interesting things with it. Here, we've been getting all sorts of spectra of exoplanets coming through the door. Here's one of the first that was observed. This is a spectrum of WASP-39b. And again, you see all these little bumps and wiggles. You can see that one of them is labeled carbon dioxide, okay? And that may sound very unexciting to you. We have carbon dioxide on Earth. And in fact, most of the planets in the solar system have carbon dioxide. What is exciting about this is that we had not observed carbon dioxide on any exoplanet ever up until this point. And that's not because carbon dioxide is rare. It's because we can't observe it with Hubble. The only way to observe carbon dioxide is by looking in the infrared. So JWST is the first telescope, well, Spitzer was able to do this to some degree, but JWST is the first telescope actually to detect carbon dioxide on an exoplanet's atmosphere. This is one of the main molecular species in an atmosphere. And so we're learning a lot now about the fundamentals of exoplanet atmospheres. We're also seeing all sorts of weird molecules and things like that in the atmosphere. So this is a planet where you can see out here, it's labeled silicates. This is basically like a layer of smoke in the atmosphere. There's some sort of almost like soot or sandy type material that's similar to, in terms of how fine-grained it is, it's similar to smoke. One of the things that we've learned that JWST has been incredibly useful for is measuring exoplanet temperatures. And the way in which it does that is really interesting. So what I'm showing you here is the transit light curve. This is the light curve of a transiting exoplanet as measured with JWST. And in the middle here is when the planet is transiting. But you can see JWST, not only does it observe that transit, it keeps observing the system. So eventually that planet goes around to the backside of the star. And when it's around the backside of the star, the planet, right before it goes behind the star, which is this little transit feature, you get to see how bright the planet is. And the brightness of that planet, if you measure that at multiple colors of light, you can deduce the temperature of the planet. And this, by knowing the temperature, you get to learn about whether there's an atmosphere there at all. You get to learn about winds on the surface of the planet. We're actually learning about the climate of planets and the motion of winds on the surfaces of these planets by measuring their temperatures, believe it or not. And we're starting to use this method now to try to figure out whether any of those potentially Earth-like planets that we know about have atmospheres. So I mentioned that we had not yet found an Earth twin around a sun-like star, but we have found rocky planets roughly the size of Earth around an M star. This is a very small star. An M star is a very low mass, low luminosity star. And so all of these planets are very, very close to it. But 3 out of the 7 transiting planets that we know of in the system are all at the right distance where they could have liquid water on their surface. This is a very exciting system called TRAPPIST-1. There's 7 planets. 3 of them have the potential to be habitable planets. We don't know if they are. And right now, what we're trying to figure out is, do they have atmospheres at all? And so we're using that method of measuring their temperature. So on the right is a press release showing the measured temperature of TRAPPIST-1b. This is the closest end planet. And as you can see, it's much hotter than what they would expect if it had an atmosphere, okay? And what that means is it is likely atmosphere free. We think that's true now for not only TRAPPIST-1b, but likely also TRAPPIST-1c. And honestly, we're not surprised. M stars like TRAPPIST-1 are very violent stars. They have huge flares and are very disruptive. And we think they might completely strip the atmospheres off of their exoplanets. So we're not sure if those 3 planets in the habitable zone around there are going to have liquid water or if they're going to be barren rocks. There are some teams working on this right now. They've taken observations of those planets. I expect in the next few months to a year or so, you're going to hear a lot more about those planets. But right now, it's not conclusive. And this ends up being a very, very extraordinarily challenging observation for JWST to make. And we're having to obtain more data to really to figure out what we're looking at because stellar activity. We now know that stellar activity is also limiting our ability not just to find transiting exoplanets, but to study their spectra and figure out what they're made of. Because as it turns out, when there's stellar activity, that means the stars are not homogeneous surfaces, and your planet might be in front of a star spot that has different molecules and atmospheres than the surface of the star. The star can even have water in its atmosphere, believe it or not. So stellar activity has really been the bane of our existence and has limited our ability to find exoplanets. If we want to find an Earth-like planet around a sun-like star, we have to go to a different type of observation. We call this direct imaging. We need to actually see the little smudge of light of an Earth-like planet. The problem is an Earth-like planet around a sun-like star is 10 billion times fainter than its host star. 10 billion times fainter. That's like trying to find a single fluorescent bacterium, phosphorescent bacterium around a spotlight, okay? And the other problem is they're separated from their host star by less than a tiny, tiny fraction of a human hair held at arm's length. So in this image, I've actually put an Earth-like planet. I'm going to see if you can find it. You probably have not found it because it's right there. Okay. You can't see it. It's 10 billion times fainter than that overwhelming star. So we need a particular type of instrument that can block out the light from the star while letting the light from the planet through. We call these instruments coronagraphs. And we've had coronagraphs for a long time. So Hubble actually has a coronagraph on it. It's using its coronagraphs to make observations like what I show you on the left. On the left, the star is at the center of the image. There's a little white spot showing where the star would be, but the image is actually blocked out in that region. So we're blocking the starlight. And you can see there's this faint ring around the system. This is Fomalhaut. This is dust. So this system has a ring of asteroids and comets, basically Kuiper belt-like objects that are producing dust. And we see the ring of dust around that system. So the coronagraphs on Hubble can't observe Earth-like planets. They can observe sort of the outer regions of planetary systems. Now, JWST also has coronagraphs, and those coronagraphs have been used to observe exoplanets. I'm showing you some images of an actual exoplanet observed with JWST on the right. The problem is JWST can only observe a very rare type of exoplanet. These are exoplanets that are very distant from their star, but also very hot. So basically, we're talking about planets that are still hot from formation, very young planets that are still cooling down. If we want to detect an Earth twin, we have to look at much fainter exoplanets, and we have to look at them right next to the host star. We're going to need a new type of coronagraph to do that. Fortunately, we will demonstrate those technologies in the next couple of years. So in 2026, the Roman Space Telescope will launch, and it is going to demonstrate many of the technologies that we need to find Earth-like planets. It won't actually find Earth-like planets on its own. It's mostly going to be finding Jupiter-like planets, but it will demonstrate the technologies we need for a future mission. One of the things that Roman will do in addition to demonstrating those technologies is it will complete, quote unquote, the census of exoplanets. So I showed you that diagram earlier that showed you this zoo of exoplanets, and more or less that kind of looked like this red region of exoplanets that Kepler has found. Well, it turns out Roman is going to use another technique that we call gravitational microlensing. It's very similar to the gravitational lensing that I showed you from the galaxy, except here it's what we call a microlensing event. And that new technique is going to be sensitive to planets that are like those in our solar system. So for the first time, we will have a space mission that can find many planets similar to our own Jupiter, Saturn, Uranus, Neptune, and maybe Earth-mass planets in the habitable zones. But if we actually want to study Earth analogs, look for an Earth twin, we're going to have to wait a bit, but not too long. In the 2040s, NASA expects to launch its future flagship mission called the Habitable Worlds Observatory. As I mentioned earlier, this is the single most ambitious mission ever taken on by NASA. We have to maintain the entire stability of the telescope. We can't let the telescope change by more than a picometer. A picometer is smaller than the radius of an atom. That entire telescope has to be stable to that level. This is an extraordinarily challenging task. We currently have many people working on how to enable that right now in the laboratory. Now, the Habitable Worlds Observatory's primary goal will be to find Earth-like planets and search them for signs of life. But when you build an instrument to do that, you have built something that, much like Hubble, can transform astrophysics over a broad range of topics. So HabWorlds is going to enable transformative astrophysics of all different kinds. To give you an idea of what it will be capable of, it is going to enable routine observation of the faintest galaxies that we can just barely see right now. So on the left is a simulation of what Hubble would see. I think this is a 50,000 second observation. I don't remember off the top of my head, of one of the faintest galaxies you could imagine trying to observe with Hubble. And on the right is what HabWorlds would see in that equivalent amount of time. And so what is currently extraordinarily challenging with Hubble will become routine with the Habitable Worlds Observatory. HabWorlds will also enable near flyby quality observations of solar system bodies. So this is an image from the Juno mission, which is currently in orbit around Jupiter. So it actually flew to Jupiter, is in orbit around there. And the resolution of this image is about 30 kilometers or so at the upper layers of Jupiter's atmosphere. The Habitable Worlds Observatory is going to have spatial resolution on Jupiter, at best 45 kilometers, probably more like 60 kilometers. So coming pretty close to the same resolution that we have from missions that are actually in orbit around Jupiter. But of course, the thing that we really want to use the Habitable Worlds Observatory for is to take an image of exoplanetary systems. And I'm going to warn you, I'll show you what one of these images looks like, but I'm going to warn you that I've shown you all of these beautiful astrophysical images. The images that we're going to get back of other planetary systems with HabWorlds are not going to be pretty. But they will be profound. We are pushing this telescope to its fundamental physical limits, the limits actually imposed by quantum mechanics. And this is what that image might look like. So this is what if there was a copy of our solar system at 12 parsecs, this is what we might see. You can see that there's dust in this system. You can see that Jupiter is very bright. And you can see the small smudge of this pale blue dot here that is the Earth. This is what we want to take an observation of. But we don't just want to observe this planet. We want to search this planet for life. Now, you might be wondering, how in the world could you possibly determine if there's life on that little blue smudge? And we have a three-pronged strategy to figure that out. The first is data quality. We are going to obtain a lot of different types of data from that smudge. One of the most important data sets is a spectrum. We're going to spread that light out into all its colors. We're going to look at the bumps and wiggles and figure out what's in the atmosphere of that planet. So if you look at the Earth's atmosphere, we can see wiggles associated with water vapor that suggests there's water in the atmosphere and therefore maybe a surface ocean. We even see oxygen in the Earth's atmosphere. Oxygen is created by life on Earth. So we consider this a biosignature gas. And if you observe oxygen as well in presence of something like methane, then you could deduce very likely that there is life on our planet. In the interest of time, I'll skip ahead here quickly. The second prong here is robust model interpretation. There is an entire field of astronomy called astrobiology, where all they do is they play around with theoretical models of planets and try to figure out what might life look like on another planet. What are things that could trick us? And so this here is a diagram showing you some of false positive scenarios that they've come up with, where they've thought of ways in which we might think we see life, in which there isn't actually life. And I'll just point to the middle one here. You can see it's labeled ocean loss by an M dwarf. The idea here is if you have a planet with an ocean on it, and it's around one of these low mass M stars that are very violent and disruptive, your water molecule, which is 2 hydrogens and an oxygen, might evaporate from the ocean, go up into the atmosphere, and then the flares from that star, the UV radiation from that star, would split the water molecule up into individual hydrogen and an individual oxygen atom. And then if that one oxygen atom combines in the atmosphere with another oxygen atom, you'd have molecular oxygen, O2. And you would have produced what we think is a biosignature gas without there being life at all. And so we have to be aware of these sorts of false positives and be able to figure out whether we're being fooled or not. Finally, the last thing is data quantity. We are going for a mission that will return a very large sample size. And basically the idea is, we didn't understand star formation by looking at the sun. And we didn't understand star formation by looking at, a dozen stars. We had to look at dozens and dozens and dozens of stars before we really had an idea of what was going on in their interiors. And the same is obviously going to be true of exoplanets. So right now we're figuring out how many planets we might want to find, and we're using software to help design the mission. That software tells us, it's able to actually simulate a survey with the mission and tell us how many planets it might find. And so here's two old concepts for the mission. We called it LUVOIR back then. And we were able to determine that LUVOIR A could find potentially 54 potentially habitable planets, whereas the other version would find 28. But not only do we want to find dozens of these potentially habitable planets, we want to find hundreds of planets of all types. So you can see if you build a mission to go searching for Earth-like planets, you will find a very, very diverse set of exoplanets. But of course, the main reason why we want a large sample size is because we're trying to answer this question, are we alone? And we want to make sure that we have a good chance of answering this question. So obviously, if we think we've found life, then maybe we can answer this. But when you think about it, if we observe a handful of stars and we don't find any signs of biosignature gases on those planets, are we going to be able to say we're alone? And the answer is no, right? There's always another star to look at. And so as it turns out, this is not the question you want to answer. And this is not what we're designing the Habitable Worlds Observer to answer. Instead, there's a very subtle difference. We're trying to answer this question. How alone are we? Because we are trying to design a mission that can find so many potentially Earth-like planets that if none of them appear Earth-like, we will be able to, for the first time, statistically address just how alone we are. And I think the Astro 2020 Decadal put this very eloquently here in their recent report, where they said life on Earth may be the result of a common process, or it may require such an unusual set of circumstances that we are the only living beings within our part of the galaxy, or even in the universe. Either answer is profound. If planets like Earth are rare, our own world becomes even more precious. If we do discover the signature of life in another planetary system, it will change our place in the universe in a way not seen since the days of Copernicus, placing Earth among a community and continuum of worlds. And to close tonight, I'd like to go back to those Greek philosophers that I brought up at the beginning. You see, most of what I talked about tonight was NASA's search for Earth-like planets. And that's a small snippet in time. But we've been asking ourselves this question for 2,500 years. And I'll have to admit to you, at the beginning of my talk, I kind of intentionally misled you. I said, how is it possible that we've all been independently asking ourselves this question for 2,500 years? And I think the answer is that we haven't. Because as it turns out, the ideas of these Greek philosophers are in your head, whether you realize it or not. And the story as to how that information made it to us today is one of the most fantastic tales I've ever heard. Because as it turns out, Democritus and Epicurus that came up with some of these ideas, these were radical ideas at the time, even in ancient Greece. In fact, I think it was Plato that said he basically hated Democritus's ideas, and he said he wanted all of his books burned. So that nobody wanted to keep the records of these guys around, right? In many cases, there were instances where the records were intentionally destroyed. Not only that, but Epicurus didn't like poetry. And at the time, a lot of these records were kept in poetic form. So Epicurus actually was not a fan of keeping records to some degree. And so for the next 2,000 years, and especially during the Middle Ages, these ideas just died off. They withered away, and very, very few people knew about them because there were almost no records of what we thought about Democritus and Epicurus. All of that changed on one day in 1417 AD, when a man named Poggio Bracciolini was at a monastic library in Germany. So Poggio is from Florence, Italy. He's a book hunter. He goes to this monastic library in Germany, and he's trying to find rare books. And he pulls this dusty old book off the shelf. That book had been written 500 years earlier in 900 AD. And it was a Latin word for Latin word copy that a monk had written of a book created much, much long ago in the 1st century BC by Lucretius. And Poggio recognized the name Lucretius, and he immediately realized he had found something very valuable. You see, Lucretius's book was titled De Rerum Natura, or On the Nature of Things. And he was an ardent follower of Democritus and Epicurus and all of their ideas, with exception of apparently one, he loved poetry, and he was an amazing poet. And so he wrote this poem called On the Nature of Things, where he talks about, physics and the nature of reality, according to these philosophers. Very dry material, you would think. But as it turns out, Lucretius is an incredible poet, and many people describe this poem as being the greatest Latin poem ever written. And they describe the language of this poem as seductive. So Poggio's reading this poem, and the contents of this poem are absolutely astounding. This poem talks about these Greek philosophers' ideas, the idea that substance stays around forever. They introduced the idea of the void. The void is space. They invented the concept of space. They talked about the fact that nothing exists except space and atoms. They invented the concept that everything is made of atoms. In fact, they invented the word atoms. This is thousands of years before the model of the atom was invented. They talk about the fact that the universe is infinite. If it's infinite, then that means there's other worlds like our own with life on them out there. They talk about the motion of the atoms, how they hook together to form molecules and you and me. They even talk about evolution in this and basically predict the ideas of Charles Darwin. They talk about natural selection. This is one of the most astounding pieces of work I have ever come across. And it is thousands of years before we had the tools to test any of this. Now, Poggio realizes immediately how profound this is. He has a friend make a copy of this book. This is the copy of that book. It's in a library in Florence, Italy right now. You can go there and request that they give you gloves and you can leaf through it, or you can do what I did and look at it online. I don't read Latin, but I did spend a night trying to translate some of this, which was beyond difficult. But after Poggio finds us, he finds us during the Renaissance era. And during the Renaissance era, people were more open to these very, very radical ideas at the time. And it sort of took off. This poem and its seductive language took off. In fact, the first person to translate this poem to English was a woman in England who was a very devout Christian, and she loved poetry, and she thought this was the most beautiful poem ever. And so she's translating this poem, and she gets halfway through it, and she decides she hates the poem. Its ideas are so radical that she thinks it's absolutely disgusting, but she finishes translating it because it is such a beautiful poem, which I think just speaks to its artistic significance. To speak to its significance in terms of how it has impacted our society, though, in ways that you probably don't appreciate, you only need to look at the people that it has touched. So not long after this poem started spreading, there was an anonymous translation of this poem. I'm sorry, not translation, a copy of this poem made. Later, it was found out this was made by Machiavelli. Isaac Newton endorses the idea of atoms long before there's an atomic model because he was familiar with this poem. Charles Darwin's grandfather directly credits this poem with his ideas, influencing his ideas on evolution. Charles Darwin claims he never saw the poem. I don't know. And then not too long ago, this poem was translated into German, and a very prominent German scientist wrote the foreword for that translation. That scientist was Albert Einstein. The list goes on and on. Thomas Jefferson owned 4 copies of this. The number of scientists and people throughout history that have interacted with this poem is truly flabbergasting. And I'm not here to say that the Greek philosophers knew all of this. They could not have known that this was right? They had no tools really to test it. This was all philosophy. But what I am saying is that their ideas have been with us for 2,500 years and have affected our reality. So whether we realize it or not, we are all part of this journey together, and we are all inheriting these ideas that have been built up for centuries. So if tonight's the first night that you've heard about the Habitable Worlds Observatory, I invite you to follow along as we develop it and join us in this 2,500-year journey. Thank you.
Thank you. I'm going to open the questions first. If anybody online wants to ask questions. Anybody, you just need to touch your mute button and talk. Okay, if nobody online wants to.
Yeah, I just want
Okay.
to say thank you very, very much for an exciting and wonderful program.
Well, it's my pleasure. Thanks for calling in.
Okay. Anybody else online? All right. How about questions from in
If I may.
in here? Yeah, Ray, go ahead.
briefly. Dr. Stark, why the incrementalism, or what appears like an incrementalism in future projects and space telescopes or observatories and within the context of the capacity to observe Earth-like planets around exoplanets? Is that technologically limited, or is there another reason?
Yeah, why are we sort of piecing this together one step at a time instead of just, why didn't we start with the Habitable World Observatory in a sense, right? So it's partly technologically, we're limited by the technology that we have. It's also partly programmatic. So when NASA decides to build a mission, we take direction from the astronomy community. The astronomy community gets together once every decade. They write a report. It's called the decadal report. I showed a snippet of that at the end, where prominent astronomers in the field basically tell NASA what it should prioritize as its next mission. And that's an extremely useful thing to NASA because it shows that NASA is not just doing what it wants to do. It is able to point to this document and say, look, this is what astronomers in the world want us to pursue. And so we have to design a mission to accomplish those science goals. Now, unfortunately, the way telescopes work, I think it's kind of easy to think that all telescopes are just tubes with mirrors, but that is far from the truth. They are an astoundingly complex system, and each one, to some degree, is unique for the science that you want to accomplish. So, as an example to illustrate that, the Hubble Space Telescope was designed before we had even discovered an exoplanet, right? But even if we knew about exoplanets, the goal of the Hubble Space Telescope wasn't to find an Earth. It was actually to measure the Hubble constant. And to measure the Hubble constant, you don't need picometer stability. And so there's just no way you're going to spend billions of dollars on trying to figure out something like picometer stability if that's not the goal of the mission, right? And so with the Habitable Worlds Observatory, for example, the goal of the mission is to find exoearths. And we know we have to achieve picometer stability to do that. And as a result, we're having to think about other aspects of the mission that allow it to be not only technologically achievable, but also cost realistic. So for example, we're pretty sure that the Habitable Worlds Observatory will not observe in the infrared because that would require us to cool the telescope. And then you have to use compressors and all these things to cool the telescope, which makes the problem of keeping it stable even harder. And so it's this whole, everything is tuned to try to accomplish the science using the technology you have at the time that the mission is conceived of.
Thank you, Tom.
Question. To what extent is the Drake equation relevant, or does it have any validity in this inquiry?
Yeah, that's a great question. So I, if in a figurative way, I work with the Drake equation every day. So my, one of my main jobs is actually doing these calculations, right? So I am the person that runs a simulation of what the Habitable Worlds Observatory might find, and we have to understand the statistics behind, that Eta Earth number I showed you, which is how many stars might have an Earth-sized rock in the habitable zone, right? And so the numbers I'm showing you here on the left, 54 and 28, those are Earth-sized rocks in the habitable zone. And we know that we don't want to, the next term in the Drake equation is the fraction of them that have, I think the fraction of them that have habitable conditions, right, that actually are habitable. So that's why we're trying to detect dozens of these rocks, because we don't know that term of the equation yet. We're trying to build a mission that is robust to a pretty low number for that term. But as I mentioned at the end, we're also trying to build a mission that if all we find are barren rocks, we will be able to quantitatively constrain that term for the first time in history. So yeah, it's very much related to the Drake equation. And if you look through history, you know, with Hubble and Kepler, you can kind of see us accomplishing, you know, measuring individual terms of the Drake equation. HabWorlds is going to take it one term further.
Thank you.
Any other questions from in here? How about online? Okay, if not, we do thank you. It was an excellent presentation.
Thank you. Appreciate the opportunity.